Quantization model in distributed systems with AWS and SageMaker. Definition. Model quantization involves reducing the precision of numerical representations, e.g., floating point numbers in machine learning models, optimizing performance, reducing memory usage, and improving overall efficiency in distributed systems for large language models (LLM) in retrieval augmented generation RAG projects. Leveraging AWS, Amazon Web Services and SageMaker. Key components: AWS services, SageMaker, fully managed service for building, training, and deploying machine learning models at scale. Integrated with AWS services for model quantization in distributed computing. EC2 instances. Elastic Compute Cloud instances for provisioning virtual servers with varying compute capacities and optimized hardware configurations. AWS Lambda, serverless computing service for executing code in response to events, optimizing resource usage and scaling model inference in distributed deployments. AWS Elastic Beanstalk, service for deploying and managing applications in the cloud, automating resource provisioning and scaling for distributed computing environments. AWS Nitro System, hardware and software infrastructure that accelerates and optimizes storage, compute, and networking tasks, improving overall system performance. Model quantization techniques. Post-training quantization applies quantization techniques after model training to reduce precision of weights and activations, optimizing model size and improving inference speed. Dynamic quantization adapts quantization levels dynamically during model inference based on input data characteristics, optimizing performance and accuracy in distributed setups. Quantization-aware training integrates quantization constraints during model training to minimize information loss and maintain performance with reduced precision in distributed environments. Hybrid quantization combines different quantization techniques, e.g., post-training and dynamic, to achieve optimal performance and efficiency trade-offs in distributed computing. Benefits: improved inference speed, accelerates model inference speed and reduces latency by reducing precision of numerical representations and optimizing computational resources through quantization in distributed systems. Reduced memory usage, lowers memory footprint and storage requirements by quantizing model weights and activations, optimizing resource allocation and improving cost efficiency in compute-intensive applications. Scalability and flexibility enhances scalability and flexibility in distributed environments by deploying quantized models that require fewer computational resources and support diverse workload demands. Cost effectiveness optimizes operational costs and resource utilization by deploying quantized models that achieve performance gains with reduced precision in distributed setups. Energy savings reduces energy consumption and operational costs by optimizing processing efficiency with quantized models, supporting sustainable computing practices in distributed deployments. Tools and technologies. AWS SageMaker, fully managed service with built-in algorithms and frameworks for implementing model quantization techniques and optimizing model performance in distributed computing. AWS EC2 instances. Elastic Compute Cloud instances for provisioning virtual servers with optimized hardware configurations and scalable compute capacity in distributed deployments. AWS Lambda, serverless computing service for executing code in response to events, automating model inference tasks and optimizing resource usage in distributed environments. AWS Elastic Beanstalk, service for deploying and managing applications in the cloud, Automating resource provisioning and scaling for distributed computing setups. AWS CloudWatch, monitoring and management service for tracking model performance metrics, optimizing resource utilization, and scaling model inference in distributed systems. Challenges: precision accuracy trade-offs, balancing model precision reduction with maintaining adequate performance and accuracy levels when implementing quantization techniques in distributed setups. Compatibility and integration, ensuring compatibility and seamless integration of quantized models with existing software, frameworks, and infrastructure in distributed computing environments. Quantization method selection, selecting appropriate quantization techniques and thresholds based on model requirements and performance metrics in diverse workload scenarios. Data integrity and accuracy, addressing potential issues related to information loss and numerical stability when applying quantization techniques to complex machine learning models in distributed systems. Training and skills, building expertise and skills in implementing and fine-tuning model quantization techniques to maximize performance gains and efficiency in distributed computing environments.